All right. Well, I guess it's a good time to start. Before we get rolling, let me remind you all about the math in tomorrow. More fun than you can shake a stick at. So be there if you get the opportunity. But it's my pleasure to introduce to you Dakota Thor Ihli, who I have known since he was but a mathematical pup. And he has been kind enough to talk to us today, and he's going to talk about how the axiom of choice can save your life.
All right. Thank you. It's great to be here speaking at the math club again after all this time. My first time at the Clemson one, I suppose. I've got some slides. Can I?
Yes, I'm sorry. I always forget that, but I've got you covered here. Let's see here. All right. Well, you should be good to go.
All right, there it goes. And share here. Does that look good? All right, cool. All right. So as promised, I will show you how the axiom of choice can save your life. Don't be afraid to interrupt me if you have questions at any point, or alternatively, you can drop them in the chat. I have the chat window up in my other monitor here. So I guess the best way to start any math talk is to start defining the mathematical terms in the title. So I guess we'll get started. So what do I mean by axioms? Okay. So suppose you have some mathematical statement that you want to actually prove. Let's say there exists an irrational number. Okay. There are many ways of going about this. You could play around with cardinality arguments or something. But one of the easiest ways to, or most convincing ways to show that there exists something is to take one of those somethings out of your pocket and show whoever it is you're trying to prove it to, wave it in front of their face like an obnoxious little brother. So let's show there exists an irrational number by proving that some specific number is irrational, right? The first number that you usually do this for is a square root of 2 in your first intro to proof class. And how does the proof usually go, right? I'll go through the entire argument here, but it usually starts as a proof by contradiction. You say square root of 2 is a over b, where a and b are whole numbers, and you assume that a and b are relatively prime, right? It's in least common terms, because you can always do this for a rational number. And then you do some argumentation. 2 is a squared over b squared, 2b squared equals a squared. And this means that a squared is even, which means that a is even. And then you replace a with 2c because it's even. You can write it as 2 times something. And you do some more argumentation, and you get that a and b must have both been even, which contradicted your assumption that they were relatively prime. Okay, so that's how the proof usually goes. And over the course of this proof, there were some calculations we did. We used this fact that if a number's square is even, then the number itself must have been even. Yeah, so a number of questions about this, right? Why are the calculations in this proof valid? Right. The reason that the calculations in this proof are valid are because we prove that they're valid, right? We use the fact that you can multiply both sides by b squared, and then the b squared cancels. The next step of this proof would be like 2b squared equals 4c squared is, 2c quantity squared, which is 4c squared. Even this like equal sign uses like commutativity and associativity of multiplication, right? These very simple facts about the arithmetic of the real numbers, that either you treat the real numbers as like some God-given object with some nice properties, or you define the real numbers from some other system and prove that it has these properties. Okay, that's why these calculations are valid, because it's based on more simpler, more elementary facts. Okay, and on a similar note, like how do we even know that there is a square root of 2, right? first of all, you have to define what this string of symbols means. This is the unique real number, which is positive and whose square is the thing under the radical, in this case 2. And you have to prove that such a thing exists, right? And is unique, that the string of symbols determines one and only one real number. And how would you show, for example, existence? Well, I remember doing this in Jim's class, right? It's application of the intermediate value theorem, which is, not just some trivial statement. It's like you actually have to prove the intermediate value theorem. And, you usually don't see an honest to goodness rigorous proof of the intermediate value theorem in calculus. You have to finally move on to more advanced, like real analysis and topology or something. Okay, so where am I going with this? The point is that anytime you want to prove something in mathematics, it is always based on something lower, right? And you can dig deeper and deeper down this chain of like simpler, more elementary facts that you use in your proofs, but it can't go down forever. It can't be turtles all the way down, right? You have to stop somewhere. There has to be a foundation, okay? And that's where axiomatic foundations come in. That's where axiomatic systems come into play. And what an axiomatic system is just an agreement that everyone makes on what are the basic bare bones facts that everyone accepts are true without proof, and then you can build on from there. Okay. And to build the foundations of all of mathematics, you need something which is simple enough that everyone can agree on what the sort of most simple properties of the system are, but also rich enough and robust enough to encode a lot of mathematics. And as it turns out, the one that we've sort of settled on over the last, I want to say 140 years or so, is set theory. And this is by no means the only possible system of foundations for mathematics that you could think of. There's things that other people do, like type theory and category theory and a lot of other stuff that I don't understand as well. But set theory is sort of the one we've sort of settled on. And once you agree on set theory, you have to define, or not define, you have to agree on what the axioms for set theory are. And again, there's no like one honest to goodness, God-given, like correct set of axioms. We've sort of agreed on some, basically through trial and error, on which ones are good and which ones are bad. And the most common choice would be a list of axioms that has a name. It's called ZF for Zermelo-Fraenkel axiom set theory, named after these mathematicians who did a lot to develop it. Okay. And I won't give you the entire list, even though I probably could, because it only contains 8 things on the list. It's actually an infinite list of axioms, but it's 6 axioms and then 2 infinite lists. And in each of the lists, all the axioms are basically of the same form. So it's really only 8 items on the list. And they're very simple statements about how sets should work in everyday mathematics. So for example, the first one is basically a definition of what it means for sets to be equal, right? Sets are equal if they have the same elements, okay? Of course, if they are equal, then they have the same elements, but the important statement here is the other direction, right? If you want to check that 2 sets are equal, it's enough to say they have the same elements. Again, like if you have a collection of sets, you can take their union, and that's also a set that you're allowed to use and work with, as long as you don't take the union of too many things, basically. Anytime you have a set and you have a property, you can take the subset of that set you started with of all elements that have that property, as long as that property is like definable in some sense. And set theory, again, is rich enough that definable is not really that weak of, or that strong of a requirement. Any set is a power set. Pretty basic stuff here. you need at least one axiom that says something exists. And the one that we usually take is just the set of natural numbers. Any infinite set would do, honestly. But the set of natural numbers is sort of the most canonical infinite set in some sense. And I said there's like 8 items on this list. I already gave you 5. So, I could have given you the other ones here, but they're really not so. One of them is called foundation, which is very technical, and you never use it unless you're like an actual working set theorist. And the others, I think, follow from some of the other ones. Yeah. The actual details of what these axioms are is not really so important, but they're all sort of like simple facts about how you expect sets to work. But axiom of choice is sort of a different animal, right? So, for example, the power set axiom, it defines what exactly the power set is. The power set is exactly the set of subsets of the other thing. But axiom of choice is sort of different. It's less descriptive. It's less constructive. It doesn't say with as much detail what set it's popping into existence. Okay, so what exactly does it say? The axiom of choice is the following statement about set theory. It says that anytime you have a collection of non-empty sets, this I here is just an index set, so you can like tell what these sets are apart. Then there's a function that picks out an element from each one. So for every index, this function takes the index and decides on an element in the ith set in your collection. Okay, and this function is a choice function. Okay, it's called a choice function because it chooses an element from each set. Okay, and that's where AC gets the name, right? It's says that you can always choose an element from each set. Okay. In other words, if you recall the notation here for the Cartesian product, which is this big capital Greek letter pi, right? This says that the Cartesian product is non-empty. There exists some element of the Cartesian product. Okay. Now, for certain specific collections, you do not necessarily need axiom of choice to show there is a choice function. For example, if there's only finitely many, you can build a choice function just by induction on the cardinality of this finite index set. Also, if these non-empty sets have some additional structure, for example, if they're groups, then you also don't need axiom of choice to show that that is a choice function, because the fact that they're groups already comes with a choice function. Just choose the identity from each one. But axiom of choice says that no matter what collection of sets you could possibly take, then a choice function must exist. Okay. Everyone good so far? Okay. Right, and so ZF by itself does not contain axiom of choice, and when you throw in axiom of choice as another axiom, you call the result ZFC. Right? 99% of mathematicians in their everyday lives, if they don't have reason to think about what axioms they're using, they're probably using ZFC, or maybe ZF with some weaker form of axiom of choice. And we'll get to some of the weaker forms later on. Okay, and why is axiom of choice necessary? So ZF by itself is pretty strong, right? It's strong enough, robust enough to define ordered pairs. Once you have ordered pairs, you can define functions. And once you have functions, then you're off to the races, right? You can define groups and rings and fields, the real numbers, the complex numbers, Boolean algebras, smooth manifolds, probability spaces, all of this stuff that, most mathematicians use. But there are some properties about these objects you can define that ZF does not give you automatically. You need axiom of choice, or at least some weak form of axiom of choice, to prove. Here's some examples of things you might want to be true. A countable union of countable sets being countable. This is not provable in ZF. You need a weak form of axiom of choice. You need the axiom of countable choice for this, which says that if you have a countable collection of non-empty sets, then there is a choice function, which is weaker than full axiom of choice, but you do need something like this. And in fact, you can't prove in ZF that a countable union of finite sets is countable. Even then, you need a very weak choice principle to prove that. Even. A nice statement from calculus. If you have a function from the reals to the reals that sends convergent sequences to convergent sequences, what I mean by that is if xn is a sequence of numbers that converges to x, then when you plug those numbers into f, it sort of agrees with the limit operator here. So if you have a convergent sequence and you apply f to the elements of the sequence, it converges to what it should. Okay. If you have a function that has that property, then it must be continuous. This, again, is not provable in ZF alone. You need, I think with this one, you also need an axiom of countable choice is enough. But you do need some choice. Also, the other direction, if you assume the function is continuous, then you don't need choice to show that it must be, this property is called sequentially continuous. But you do need choice to show sequentially continuous implies continuous. So another fact about cardinality, for all sets x and y, one is bigger than the other. Okay, you need full choice to say this for all sets x and y, which means if you didn't have choice, it might be the case that you have two sets whose sizes are incomparable somehow. The very idea of using cardinality to measure size kind of breaks down in that case. So a nice fact from linear algebra that every vector space has a basis. Again, you do not need choice if the only vector spaces you worry about are finite dimensional. But once you move into infinite dimensional vector spaces, which many mathematicians do when they study like Banach spaces or any of these crazy other objects, having a basis, you need choice for this. All right, so I knew Jim was going to be in the audience, so I had to throw in an algebra fact here. You need choice to say that every commutative ring with identity admits a maximal ideal. Okay. And you don't need commutative here. It's just if you remove commutative, you have to specify whether you're talking about left and right ideals. If you know any combinatorics, then you may have heard of the infinite Ramsey theorem. I won't get too far into it. If you know it, you know it. If you don't, it's not that important. But it's the statement that if you have like a collection of k element subsets of the naturals and you color them with n colors, then there must be some infinite subset of the naturals, which is monochromatic. Again, if you've never heard of this, it's not that big a deal. I just wanted to give a list of theorems from a wide variety of areas of mathematics to show just how pervasive axiom of choice is in really all mathematicians' lives. If you study topology or analysis, then you know the bare category theorem, which says that for any complete metric space, any countable collection of dense open sets has a dense intersection. the same for locally compact Hausdorff spaces. Again, this is dependent on a weak form of choice. And actually, you can sort of measure in terms of strength how strong each of these statements is. It turns out that these three are actually equivalent to axiom of choice, meaning if you assume any one of them, you can prove axiom of choice as a theorem and vice versa. Let's see, these, I want to say these are strictly weaker than axiom of countable choice. Axiom of choice with a little subscript lowercase omega. This one is even weaker than axiom of choice, axiom of countable choice. This one is equivalent to something called the axiom of dependent choice. I'm not going to define what dependent choice is. Just the point I want to make is that there's a whole zoo of choice principles. Axiom of choice is like the strongest one, and it has these sort of nice structure properties about vector spaces and cardinalities and stuff. So people often have no problem with assuming the stronger one, but you can sort of rank all these statements in a hierarchy of how strong or weak they are, which is sort of interesting in and of itself. All right. Yeah, and one thing I want to say is that for a lot of these ones that are sort of existence statements, like this one about every vector space having a basis, once you have one, you can, using just statements about ZF, prove the existence from the one of many others, right? If you have some complicated vector space, once you use axiom of choice to say it as a basis, then you can use that one like spooky basis you pulled from the ether and use it to build all sorts of other ones, right? I expect that if you have a commutative ring and you pull a maximal ideal out of thin air using choice, then you can use it to get others. I'm not actually sure on that. Maybe Jim can confirm or deny. I know there's like local rings where there's like the maximal ideal is unique.
Whoops, there. That's true. I mean, you could certainly. I mean, but of course, again, it's just like you know, when you have a local ring, you sort of come with a choice function because there's only one maximal ideal. But there's certainly some examples where, like for example, if you look at a direct product of a field with two elements, it's got very ugly maximal ideals, and I'm sure you can use the axiom of choice to come up with others. Mm-hmm. Isn't another thing? Don't you need the axiom of choice to show that any infinite set has a countable subset?
Yes, you need axiom of countable choice for that.
Yeah.
Yeah,
I always thought it was weird.
I forgot about that one. I meant to add it on here actually, but yes, I'll add it here. Any infinite set has a countably infinite subset. Actually, having a countably infinite subset has a name. It's called being Dedekind infinite. And it's actually equivalent over ZF to being in bijection with a proper subset of yourself. Is actually equivalent, which is, yeah, it's shocking that without choice, it's in honest to goodness, like different property than being infinite. Right. Right, so this list of things, these are things that we kind of want to be true, right? They're very useful structure theorems. Like myself, I study things called Polish spaces, which are complete metric spaces. And the bare category theorem, I use it all the time, like statements about bare category are like my bread and butter. So if I lived in a world where dependent choice wasn't true, I would be in a world of pain. So we want these things to be true. We want axiom of choice around. And it has another thing going for it, which is that it is consistent in some sense. What do I mean by that? So an axiomatic system is consistent if it doesn't prove a contradiction. And if there is no possible way you could start from the axioms and write a finite length proof of like 0 = 1. This is obviously a good property for an axiomatic system to have, because if you could prove a contradiction, then you could prove literally anything, which sounds useful, but it's not mathematically interesting, because intuitively we think some things should be false. And it turns out that axiom of choice is consistent relative to ZF, meaning that you can't start with ZF and then prove that axiom of choice is false. This is a theorem of Girdle, one of the gods of modern mathematical logic, from the late 30s. And this means that if ZF is consistent, so is ZFC. And the benefit to this is that if you believe that ZF is consistent, which most people do, there's another more famous theorem of Gödel that says you can't really prove that it's consistent. But if you believe it is, which most people do, then you shouldn't have any philosophical issues, at least from a provability standpoint, in assuming choice as well. Okay. And we'll come back to this near the end. Right. So if choice is so useful, and there's this sort of technical, like ontological evidence that assuming it is not a problem, then what's the big deal? Why did I, in my abstract, and Jim in the advertising emails, say that choice has some sort of controversial status as like non-intuitive? Right, so what's the issue? The issue is that ZFC, ZF with choice, proves some very intuitive things, but also some not so intuitive things, right? So the sort of canonical example of something that is that you need choice to prove, that is not, that people have problems with, is the Bon Aktarsky Paradox, which this sort of glib way of putting it is that one ball is two balls. What do I mean by this, if you've never seen this before? It has paradox in the name, but it is a theorem. It has a completely correct proof from ZFC as the axioms. It says that if you have, say, a unit ball in 3D space, that there is some finite partition, so you can break it into finitely many pieces, and it's not even that many. I think it's like 5 or something. That when you split it up, and you can take those pieces, and you can move them around using just rotations and translations. You don't have to stretch them or bend them or anything like that. And you sort of move them around such that at the end, when you're finished moving them around, you have 2 spheres the same size as you started with. Right, so you take a ball and you like cut it into finitely many pieces, and then you put them back together, and all of a sudden you doubled what you started with. All right, this theorem is actually the proof that Jesus of Nazareth must have been pro-choice. And the reason for this is that in all 4 of the Gospels, Jesus is recorded as feeding 5,000 people with 5 loaves of bread and 2 fish. And that's how you know that he's pro-choice, because this is the theorem that he must have used to do that. If you know anything about the proof of this theorem, you have to use non-measurable sets, and I guess maybe that's where his divine touch comes in.
Right, because that's very specific, isn't it? That it has to use sets that are not measurable, right?
Right.
But only finitely many.
Mm-hmm. Right. And the non-measurable sets come up in a similar way to what I'd like to show you in a minute here. But before I move on, I just want to say, if you want to know more about this, there's the most viewed Bon Aktarsky Paradox video on YouTube. It's this by this channel called Vsauce. He's been doing a lot of mathematical stuff lately on like infinite ordinals and some cool stuff. And he also made a series on like philosophy or psychology or something. But it's called Bon Aktarsky Paradox. The thumbnail is just like a exploding star on a black background. It's a good video. I'd recommend. Right. So I also advertised that you can save lives with this axiom. And what do I mean by this? So here's the setup, right? It's a puzzle. Suppose you have a countably infinite sequence of prisoners on death row. Okay. So the first time I gave this talk, it was late 2015. It was at the math club at North Dakota State, my undergrad. And I made this joke where the prisoners are all mathematicians because the year is 2022. President Trump made mathematics illegal. And this was, back when the notion that Trump could become president was not only a joke, but a joke that would elicit a laugh from the audience. So I guess I jinxed it there. But in any case, we have a infinite number of prisoners on death row. They're all given an ID number, a natural number on like their lapel. There's prisoner 0, prisoner 1, prisoner 0, there's prisoner 1. There's 1 for every natural number. So here's prisoner 24601, and so on. And the warden, right before they're all executed, they're all waiting in line for the chair. And the warden decides to be a little sadistic and have some fun with them. And he decides to give them a chance at survival. Okay. And the warden, you can imagine some sort of Yosemite Sam type figure who says, here's the game we're going to play. I'm going to give all of you a colored hat. And if you correctly guess what color your hat is, I'll let you go. Okay. Yosemite Sam thinks, like half of these people are goners. At least half. But Yosemite Sam forgot to consider that all these prisoners are mathematicians. Okay, so here are the rules of the game. The prisoners line up in a queue. So they all face forward, and they're all looking forward at the next person in line, so that everyone sees all but finitely many of them. So prisoner 0 sees everyone but himself, prisoner 1 sees everyone but himself and prisoner 0, and so on. Okay, so they're all facing this direction. Right. And what the warden will do is he's going to give everyone a colored hat. I have to do this copy paste game with my drawing here. For right now, he just chooses between red and blue. Okay, so prisoner 0 gets a blue hat, maybe prisoner 1 gets a blue hat, maybe prisoner 7 gets a blue hat, maybe 24601 gets a blue hat, and then everyone else gets red hats. So like player prisoner 2 gets a red hat, prisoner 5 gets a red hat, prisoner 406 gets a red hat, and so on. So everyone gets a colored hat. Okay. And then everyone guesses. Way back in the day, I had to come up with some convoluted rules, like everyone says what their hat is, but they're deaf and can't hear the other answers. And then I did a Google and I saw that Clemson also uses eye clickers, so I could just say everyone guesses their hat color on an eye clicker, right? And everyone's got these remotes that large lecture classes use to collect answers from students in large lectures. And everyone guesses at the same time what their hat is. Okay. And if they guess correctly, then they get to go free. But if they guess incorrectly, then a trapdoor opens beneath them and they fall down a chute into like an alligator pit. Okay. And no one can see each other's guesses because everyone's eye clickers are sort of huddled over, can't really see over their shoulders. But everyone can see the hats on the people in front of them. Right? Person 0 can't see his own hat, but he can see that prisoner 1 has a blue hat. He can see that prisoner 2 has a red hat. He can see that prisoner 24601 has a blue hat, and so on. Prisoner 2 can't see that 0 or 1 have blue hats or that he has a red hat, but he can see everyone in front of him, and so on. These prisoners have very good eyesight. They can see like infinitely far in front of them. So everyone can see like many of the hats, but they don't know what each other's guesses are. And they're allowed to agree on a strategy the night before. Again, Yosemite Sam doesn't see any problems with this setup. Yeah, sure, talk amongst yourself, who cares? Right? So how can they maximize their chances of survival? Is it possible that they have that each person has a better than 50% chance of guessing correctly? Take a moment to decide for yourself whether you think this should be possible or not. Obviously, there's the meta reason that if I'm framing the question this way, obviously they must have something up their sleeve that has to do with the axiom of choice. But yeah, so here's what they do. So symbols are easier to deal with than colors. So let's just call a blue hat a 0 and a red hat a 1. Okay. And when the warden assigns a sequence of hats to everyone, he's choosing a sequence of 0s and 1s. Right. So pull up this picture we had. What he's really doing is, he's choosing like this is 0, 0, 1, and then whatever this is 1, and then 0, and then 1, and then 0, right? And so this gives some nice symbols to attack the problem with. And if you want to collect all of the infinite sequences of 0s and 1s into like one nice little space, this is the how we usually denote it. It's just a 2 to the superscript lowercase omega. The 2 refers to the fact that there are 2 hat colors, and the omega refers to the fact that there are infinite sequences. I'm a logician, and logicians like to represent the natural numbers with the lowercase letter omega. Just sort of a quirk we have, I guess. We have good reason for it, but okay. And now I want to define a relation on this space of infinite sequences, right? For 2 sequences, I define them to be similar. I use this twiddle symbol to say that they differ in only finitely many places. Okay, so for example, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, ... and 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, ... If you assume that these are completely the same from then on, then these 2 sequences are related, right? Then X and Y are similar. Okay. Yeah, and if you recall this terminology, this is an equivalence relation, right? Every sequence is similar to itself. If X and Y are similar, then Y and X are similar because you're just looking at the places where they differ. It doesn't matter which one you look at first. And also, if you have X and Y that are similar, and y and z that are similar, then x and z must also be similar. Why is that? Because x and z differ in only the places where x and y differ, plus the places where y and z differ, or maybe fewer. Okay, so it's reflexive, symmetric, transitive. It's an equivalence relation. And it's an equivalence relation, so we have equivalence classes, right? If you don't recall this terminology, it just means that you take, for a sequence, the brackets around the sequence just denotes the set of all things that are equivalent to it. Okay, these are called equivalence classes. And recall the sort of best property about equivalence classes, which is that they're the same precisely when the things on the inside of the brackets are similar to each other. And this is also the same as saying that they have non-empty intersection. So if they intersect somewhere, then it must be because they're actually the same. Right? So this relation gives you some equivalence classes. These are non-empty sets. It's a collection of non-empty sets. You know where I'm going with this? So what the prisoners do, how are they able to cheat the system? So the night before, they pick one element from every equivalence class. And this is sort of really the heart of every non-intuitive result that follows from axiom of choice. They all follow from choosing one representative from an equivalence class for some equivalence relation. The same is true for Bon Aktarsky Paradox as well. Like the reason that works is because at some point you take one element from each equivalence class of some equivalence relation. And you do the same here. The equivalence relation is this twiddled relation from the last slide. So they pick one element from each equivalence class and they memorize the list the night before. And now what happens when the warden assigns a hat sequence W? Do I still have? Yes, I do. Okay. When he assigns this sequence W, let's say that he assigns this sequence W, W for warden, right? What can, say, prisoner 2 see? Okay. He can't see 0, he can't see 1, and he can't see his own hat. But he can see everyone in front of him. So he narrows down the possibilities to like 8 of them, right? Whether this guy has a blue or red hat, whether this guy has a blue or red hat, or whether he has a blue or red hat. It's like 2 to the 3 possibilities. But all of those possibilities are in the same equivalence class, right? Because they're all equal on this sort of tail here, this tail of reds and blues. And so prisoner 2 now knows what equivalence class the warden's hat choices is in. He doesn't know what the first couple hats are, but he doesn't need to. He knows what equivalence class it's in. But there's nothing special about prisoner 2. Same for prisoners 0 and 1. Same for prisoner 47, for prisoner 24601. Everyone can see what equivalence class the warden's sequence is in, even if they can't see the entire sequence. Okay, so they now know an equivalence class that's sort of special here. And they remember to last night, oh, we memorized one and only one equivalent, like representative from this equivalence class. So let's just guess according to the one we memorized. Right? The prisoners can see what equivalence class W is in. So they guess according to whatever the sequence in the equivalence class that they memorized, that they call P for prisoner. And then we'll see what happens, right? What happens is that because it's in the equivalence class of the one the warden chose, it differs from whatever the warden chose in only finitely many places. It might be a large finite number, sure. It might be like 48 million prisoners, but only a finite number, which there's infinitely many prisoners. So if only finitely many are guessing wrong, that's still pretty good, right? Because even like 600 billion is way less than an infinite cardinal, right? So almost everyone lives for an appropriate definition of almost everyone. So I hope that if this is the first time you see this puzzle, this is not what you expected to happen when I posed the problem at the beginning. Okay. So I have some remarks about this. So I started by saying red and blue hats. What if the warden tries this again with another batch of infinitely many prisoners, and he throws in a green hat this time, and maybe also some yellow hats? Okay. The prisoners can run the exact same argument. They memorize another list of representatives from each equivalence class for the equivalence relation of being equal on all but finitely many places. And it works for any set of colors, not just red and blue. Like the warden could throw in green and yellow and magenta and a slightly darker shade of green, and he could call up Crayola and say, I need infinitely many colors stat. Like any even uncountable set of colors, this still works. The only difference is the prisoners have to memorize a longer list of sequences, but they already had to memorize like infinitely many, so this is maybe not much of a stretch. Now, how can the warden beat this? I showed that he can't get infinitely many prisoners to die. Like their strategy is just too good. But what if the warden like hides a microphone in the room that the prisoners are agreeing on this list on, so that he knows their memorized list? Then he can't guarantee that infinitely many guess wrong, but any finite set of prisoners, he can force them to guess wrong. So if the warden is not Yosemite Sam, but like, Javert, then he can guarantee that 24601 guesses wrong, because whatever sequence he chooses, he just flips 24601's hat from the one he knows he's going to guess. And also 24601's friends and everyone that came before him, and like the next 1,000 people that come after him and so on. But that's really the best the warden can do. And now another thing that I want to mention, the list that the prisoners are memorizing is a subset of 2 to the omega. This is a statement about topology and analysis, so if you're not so familiar with that area, you can ignore this part. But if you do know about this area, then this is maybe of interest to you. They memorize a list, which is a subset of this 2 to the omega. 2 to the omega is a nice topological space. It's a nice compact Hausdorff space. And there's also a nice measure you can put on this space. You take the topology is you take the product topology with respect to the discrete measure, the discrete topology on the 2-element set. And then the measure is you take the product measure with respect to any measure on the 2-element set, like the you could have the so-called Bernoulli measure, where 0 and 1 have the equal probability. So in both this topological sense and this sort of measure theoretic sense, this set they memorize can't be measurable, like period. I'm actually second guessing this. I believe this is true. This set is definitely not Borel. I absolutely know that, but whether it's non-measurable in a topological sense or non-measurable in a measurable sense, I think there's some detail about whether they're meager or null or something. But the set they memorize no matter what it is, it can't have nice topological or measure theoretic properties. It has to be bad. And this is relating back to the Bon Aktarsky paradox. The reason that worked is because these sets that you break the sphere up into are non-measurable. They're, from a topological sense or a measure theoretic sense, they're very bad. And the same sort of phenomenon happens here. Okay. So can choice fail? Can we like stop this nonsense from happening with like non-measurable sets and stuff? So remember this theorem from a few slides ago of Girdle that Zf can't prove that choice is false. It turns out that kind of the opposite is true, that Zf can't prove that choice is true. Right, this is a theorem of Paul Cohen from the 60s. This is a result of him developing a wonderful technique in set theory called forcing. So Zf can't prove that AC is either true or false. And what this means is that choice is what's called independent of Zf. If you know anything about Euclidean geometry, it's very much like Euclid's parallel postulate. AC is to Zf set theory as the parallel postulate is to like plane geometry, where if you assume that it's true, then you get some kind of theory, and if you assume it's false, you get some other kind of theory. In geometry, if you assume the parallel postulate, you get nice Euclidean geometry, and if you assume the negation of the parallel postulate, you get hyperbolic geometry. And when people realized that this could happen, like people started studying hyperbolic geometry and a lot of interesting mathematics happened. And the same can happen here. So what does set theory look like if axiom of choice is false? A lot of things, actually. Since I'm running low on time, this list will be rather short. So it is possible, if choice fails, that a countable union of countable sets is uncountable. And in fact, it's possible that the real numbers themselves is an example of something that can be a countable union of countable sets. This doesn't say that R is countable. This just says that R is an uncountable set that is nevertheless a countable union of countable sets, which is kind of wild to me. It is also possible that if choice fails, there is a vector space that has two different bases, and these bases have different cardinalities. They are not in bijection with each other. This can only happen if the vector space has infinite dimensions. What this means is that dimension doesn't even always make sense in this context. So linear algebra becomes a very different area of study. So these bad things could happen, but it's also the case that it's possible, if choice fails, that all subsets of the real numbers are measurable. It is also possible that not only are all subsets of the reals measurable with respect to Lebesgue measure, but they also have the property of Bayer, which is like a topological version of measurability. And they have what's called the perfect set property, which is basically the continuum hypothesis for subsets of the reals. It's stronger than the continuum hypothesis in some sense. And it is possible that all three of those things I just said are true, but you still have some choice in the form of the Bayer category theorem, this dependent choice that I mentioned earlier. And dependent choice is basically enough choice to still like do most of real analysis. So this theorem that I said, where it's possible that you have dependent choice, so you can develop most of analysis, and all sets of the reals are measurable and have like this perfect set property business, very nice. This is a theorem of Solovay from the 70s, I believe, and it's a very famous and deep theorem that depends on some very strange other set theoretic assumptions about large cardinals and stuff. Yeah, so I believe that this slide is a copy of what's before, and that is all I had for you. Thank you very much for your attention.
All right, let's thank our speaker. Thanks, Dakota. It was a great talk. Okay.
Thank you.
Anybody got any questions?
I think I have a quick question. I think whenever I like the story you're showing with the little problem with the prisoners, so that was pretty interesting. But I think I got a little lost at one point. So like, what are they memorizing exactly? It's like is it a list of equivalence classes, or is it just like a string? So like 0, 0, 1 and like random string.
They're memorizing a list of elements from each equivalence class. So, so say 0, 0, 1, 0, 0, 0, and like, so, so the string of just all zeros, they memorize one element from this equivalence class, and they memorize one element from this equivalence class. So they memorize one string where it just ends in all zeros. They memorize one string where it ends in just all ones. They memorize one string where starting from some even place, it's 0, 1, 0, 1, 0, 1.
Okay.
They memorize one where it's 0, 0, 1, 0, 0, 1, 0, 0, 1, and so on. There are some like non-periodic ones where it's like 0, 1, 0, 0, 1, 0, 0, 0, 1, and so on. So every possible sequence of zeros and ones, they memorize a list that is just so that no matter what the warden picks, it is similar, it's twiddle related to exactly one of the ones they memorized.
Okay, that makes a lot more sense now.
Yeah, and the reason they can do this is just a fact of equivalence relations, which is that the equivalence classes partition the thing it's an equivalence relation on.
Okay. All right, awesome. Thank you so much.
No problem.
Okay. Any other questions? I have a quick question. How complicated is it to show that something like choice is independent of the other ZF axioms?
So you have to be familiar with some amount of model theory, which is usually like a semester-long course. But you probably don't need like all of the semester-long course. So I can sort of explain what the idea is, like with what you need. So take, for example, not set theory, but group theory. Set theory has like infinitely many axioms, but like they all sort of are like a list of 8 many things. Group theory has exactly 3 axioms, right? There's for every x, for every y, for every z, x times y times z is, there's associativity, x times y times z. And then there's for every x, x times 1 equals x. And then there's for every x, there exists a y such that x times y equals 1. Right, so these are the axioms of group theory.
You also need closure, I guess.
Yeah, closure in the setup of model theory just comes for free. Like all operations are assumed to be closed. And so this is a list of axioms, which I'll call gr. And now I write down a statement that says for every x, for every y, x times y equals y times x. Obviously, you cannot prove from these axioms whether this is true or false. you can't prove that it's true. And how do you know? Because you can find a group
Right.
for which it's not commutative.
Mhm.
But you can't prove that it's false because you can find a group where it is commutative.
Mhm.
And so being abelian is independent of the axioms of group theory. Axiom of choice is sort of a similar sort of beast. If you assume that ZF is consistent, meaning it doesn't prove contradiction, then there's a wonderful theorem of Girdle called Girdle's completeness theorem, which is different from the incompleteness theorem, that says that any consistent theory has a model. A model just means some set, we'll say M, and some interpretation of all the symbols that it uses. For groups, the symbols it uses are the multiplication, which is a binary operation, the 1, which is a constant symbol or a zero-ary function symbol, and then inversion, which is a unary function symbol. The multiplication is also a binary function symbol, not relation symbol. For set theory, there's just one relation symbol. It's this thing, the element of relation. Everything else can be defined in terms of the element of relation. Okay. And so Girdle's incompleteness theorem says you can't really prove that ZF is consistent, so we don't really know if models exist, but we all believe that it's consistent. So you can assume that a model exists. And then once you have a model, you can use it to define other models that maybe have other properties. And so this is what Girdle did to show that you can't prove choice is false. Within just any model of ZF, you can pick out a nice subset, which is also a model of ZF. It's kind of like taking a subgroup. You find a submodel of set theory that also has nice properties. And one of these nice properties is that even if choice wasn't necessarily true in the big model, it is still true in the small model. The actual model that he defined is called Girdle's constructible L. So constructible, if you're interested, this is what you want to Google. Girdle's constructible L, constructible universe. It also satisfies some nice things about the generalized continuum hypothesis. If you know what the continuum hypothesis is, this also relates to that as well. So this is what Girdle did. Now, Paul Cohen, when he proved that choice can't be proven by ZF, he developed a technique called forcing. And forcing is much more difficult to describe, but the best way I can explain it, I can really only make an analogy to that works if you have taken like second semester abstract algebra and you know about field theory. If you have a field F, working outside of this field, you can sort of adjoin a new element, which is transcendental over F. Or maybe it's algebraic, but the point is F can still say some things about the element U that you adjoin, even if it doesn't have an element U itself, it can still like talk about U. It can say whether it's like algebraic or transcendental or something. It's like F is like us in the real world, and this transcendental element is like Bigfoot. Like we can talk about Bigfoot, but we don't have a Bigfoot because Bigfoot's not real. But we can still like describe Bigfoot without looking at him. And this is sort of closer to what Paul Cohen developed. He developed a way to adjoin sort of mysterious outside elements to a model of set theory to get a bigger model of set theory that has other properties. And he was able to use this to show that if you start with a model of ZF, you can get a model of ZF plus choice fails.
Okay. Well, thank you very much. Anybody got any other questions?
Me, again about the prisoner example.
Mhm.
Can you remind me what was the cardinality of that strange 2 to the omega?
So 2 to the omega is cardinality continuum.
Continuum. Yeah.
So their cardinalities are the same as the reals.
Mhm.
And in fact, a logician sometimes refers to elements of this set as reals, which some other areas may object to.
Mhm.
But in some sense, these are very similar objects. And in my area, they might as well be the same object.
Right.
Didn't you say that 2 to omega is not even Borel set or something? Huh?
So the list of sequences that the prisoners memorize, this transversal for the equivalence relation, this is not a Borel set.
Okay.
Yeah. Yeah, so this P that the prisoners memorize, this is a transversal.
Right.
For this twiddle relation. This is not a Borel set, and I believe that it's also neither measurable with respect to whatever the first non-trivial measure on the space that you think of. That's probably the right one. It's not measurable with respect to that measure, and it also does not have the property of Baire, meaning it is not a symmetric difference with an open set is meager, which is sort of like a topological version of measurability.
Is the cardinality of 3 to the omega bigger than the cardinality of 2 to the omega?
They are the same.
They're the same.
And in fact, this is equal to the omega. And in fact, this is equal to omega to the omega. So sequences of natural numbers. So any countable set, finite or infinite, the set of sequences of the set of countable sequences of that set is cardinality continuum.
All right. Other questions? Any others? Well, let's thank our speaker one more time. Thanks so much, Dakota. That was great.
Yeah, thanks for having me.
You all stay safe. If I don't see you, have a good summer, but hopefully I'll see you at the math end tomorrow. Other than that, y'all have a good one.
You too.
Got him.